Okay, so now we get to the heart of Strevens's theory. The method that science uses to transcend the subjective biases of individual sciences. And he calls it the iron rule of explanation. The basic idea is this. In science, the only thing that counts is empirical evidence. Stephen Hawking, all I'm concerned with is that the theory should predict the results of measurements. Another famous physicist, Richard Feynman, who's in here, experiment is the sole judge of scientific truth. So the iron rule says that the only thing that counts when you evaluate a scientific theory is empirical evidence, observations. Does it predict measurements you can make? Does it predict observations you can make in nature? That is the only thing that counts. So whether the theory is elegant, as Eddington thought Einstein's was, whether it's beautifully unified, which is something that distinguishes good science according to Kitcher, whether it's beautiful or whether it creates, it's philosophically coherent, for example, with other parts of science, with our values and so on, those things all count for nothing in science. So what's distinguishing is important here is the only. Philosophers like Aristotle, as Strevens points out, they also were interested in empirical evidence, in observations, in measurements. But they also added theoretical elegance, unity, beauty, and philosophical coherence. What distinguishes science is that those things don't count. Now, of course, you might react that scientists do use philosophy, beauty, and elegance all the time. And Strevens describes these things in his book. So Eddington, as we saw, did that. He believed partly because that Einstein's theory is right, because it was such an amazingly beautiful, unified theory. And it is really. I mean, the general theory of relativity is absolutely, the basic idea is absolutely beautiful. It shows a certain kind of symmetry that one feels like it has to be true. And then Strevens describes other scientists. So Gell-Mann is the person who first proposed the theory of quarks that make up this atomic particles. He had developed a system. Part of what was driving it, and this is like a book about this, driving him is that this would organize this weird field of subatomic particles in a beautiful system. And that was very much driving him. As a scientist. So scientists are driven by these ideas of beauty and elegance all the time. They're also driven by, they're using in their methods also various mind-bending techniques. Someone that I've learned recently about is Kary Mullis. So Kary Mullis is the person that discovered the PCR technique. Polymerase chain reaction. And that's probably some technique that you have heard about because it's used to test for the coronavirus, among other things. It's when you get a coronavirus test, you can then get a quick test, which is sometimes not the PCR test, not so precise. The PCR tests are a lot more precise. It's not used just for the coronavirus test, it's used all over molecular biology and medicine, and in a certain way you can really say there's a period in molecular biology before PCR and after PCR. This is like a very different thing. It was discovered by Kary Mullis, who is, let's put it mildly, a wild character. He describes how he discovered it in this book, Dancing Naked in the Minefield, where he talks about driving down some California. So he was a surfer, driving down some California roads and having these wild kind of like images of dancing molecules. And then he calculated it from there. He calculated, he then sort of imagined how these things could come together. And when he went back to the lab, he kind of had it all like figured out, and he's like discovered the PCR technique. He himself, and this is, I'm not absolutely sure that this is an accurate quote, but he said, if I had not taken LSD, would I have still invented PCR? I doubt it. I don't know. I doubt it. I seriously doubt it. Okay. He thought that the kind of creative imagination and his kind of imagery was very important for discovering PCR. Okay, they use that, scientists. They don't just use, it doesn't seem they don't just use empirical evidence, they use those things. Lynn Margulis, the discoverer of the endosymbiotic theory that changed evolutionary biology also dramatically, also appeals to the certain elegance in her theorizing. And Strevens gives lots of other examples where scientists appeal to that. And he has a chapter in the book where he also argues that beauty, elegance, and coherence, in fact, often are guides to truth. In not just in philosophy, but also in science, they are guides to truth. So someone like Aristotle, who the philosophers would like to have a coherent, unified, beautiful system of the world, they're right. These things are important. But in science, only empirical evidence counts. In what sense then is that true? In the sense that, not in the sense that scientists don't use that, is that you cannot publish a scientific paper that appeals as its main argument to beauty coherence. The scientific paper, that's what it is to produce a scientific paper. It must attempt to explain some observations or experiments or make some predictions that could be then tested in observational experiments. The scientists might well believe in something because of its elegance, or scientific theory or research program might be accepted widely because of it. It's beautiful, say. But you are not allowed, you cannot appeal to such things as beauty in an official scientific discussion. So it's this specific sense in which only empirical evidence counts, that it's the only thing that counts in the official discourse of science in the papers. Okay, so then we come to this iron rule of explanation. So as a first pass, it just says resolve differences of opinion only by appealing to empirical evidence. So in the book, he has, in the chapter that you've read, he has this imaginary kind of dialogue between two scientists and how they test the theories, and they propose, let's make a test. And so more precisely then, what you'll try to do in science is just try to settle all arguments by empirical testing. That's the goal. And what's an empirical test? It consists in an experiment or a measurement where the outcome will be explained by one hypothesis plus the protective belt of that hypothesis, but not another hypothesis. Okay. So this is what Eddington did. He went out, tried to form a test that would test Einstein's versus Newton's theory. And you can use now all kinds of appeal to the protective belt in order to decide this. But what's distinguished of science is that that's what you have to do. You have to do empirical testing. And that's the only thing you can do. That's what makes it different from the alchemists. The alchemists do appeal, like the scientists too. They do experiments, but they don't use it in that way. It's not the only thing that can distinguish, that is allowed to decide between hypotheses. They appeal to all kinds of other things. Now, why is that iron rule irrational? What Strevens argues is that it violates something that he calls the principle of total evidence, which goes back to the philosopher Rudolf Carnap. And that is this. When deciding an important matter, you should take into account all relevant considerations. So Carnap formulated a bit more like this. You must use all available evidence when estimating whether something is true. When you estimate whether a theory is true, you should use all available evidence. It's irrational to just disregard some evidence. Now, why is that then? Why is it irrational in that sense? Because philosophical coherence, beauty, and so on can also be relevant, and that's why all these that's why Strevens goes through a lot of detail to show that it is relevant. Now, note this iron rule doesn't say that it's irrational to prefer empirical evidence over aesthetic appeal. That might be very rational. It might be that it's more important, more relevant. What's irrational is that you toss out a whole range of considerations that could be relevant. It's like Sherlock Holmes trying to figure out who committed a crime, and he says, well, I'm not talking to any witnesses, or I'm only talking to witnesses. I'm not looking at all what happened, or I'm not considering say what the dogs did that night. And that seems irrational. I mean, if you're trying to find out what's true, you need to use everything. In the right iron rule forbids you to use everything. Okay, but why then? What's so good about it? What's so good about this iron rule if it's irrational and if it goes against, for example, the kind of impulse that philosophers have? What Strevens argues is that you can't see that in a single scientist, but you see it over time. It makes scientists search for empirical evidence at all costs. And that over time leads to an accumulation of many, by itself dull, but ultimately significant findings. So these dull observations from Eddington in this paper, that in the end he said like, well, they're explained by some weird things about the telescope. We have these data. We have in the middle, you see observations from Galileo when he observed the sun. We have his drawings. So it's science. You make experiments, you put them into, you collect them in papers, and they come out in studies. And these studies have thousands and thousands and millions of observations in it. And while scientists might not agree what these observations show, they are observations and they can be used in new ways in the future. And this amasses experiments that are in these experimental results in certain sense transcend this particular scientific use they were initially conducted for. So Strevens uses this absolutely beautiful metaphor. Yeah. So imagine a coral reef, like this is the Great Barrier Reef, the greatest coral reef in the world. And the coral reef is a result of these tiny, tiny organisms, these polyps that you see on the left here. And they leave behind skeletons. Each of them has a short life and does whatever it does. But the reef is generated by its leftover skeleton that's dead. And that's what Strevens thinks science does. Each scientist does this little thing. It's like a little polyp, but they leave behind this massive amount of data that are collected through the iron rule that tells you have to collect data. And that's shaped this big, big constructions that is modern science. So the result of the iron rule, a bit more precisely, is that scientists, while they disagree on everything, on many things, they have different political values and influences how to do science and all that, they have a procedural agreement. That is, Strevens calls a shared rule of engagement. They agree that that's the way you need to resolve the disagreement. And that's very different from, for example, religion. And often if you have a clash between two religious beliefs, they don't even agree what would decide who's right. They have no agreement about that. And so you get these groups living completely independently of each other. That doesn't happen in science. That you will not just have a group of scientists that never talk to the other because they still agree. We should try to find an experiment to decide between these theories. So it ensures a kind of continuity over time. There's no schism in science since Newton. And it leads to data, as I said, as a valuable byproduct. So again, the coral reef metaphor. It fixes rules and leads scientists to focus on producing those data. So it's important. It tells you these are the rules, and now we're playing the game, and you just have to conduct an experiment. In philosophy, we're always talking about what really are the rules? What is a good philosophical theory? How do we decide what philosopher is right? We don't know. It's complicated. Science is not in that sense complicated. Everyone agrees that this is the rule. And it's also important though that the rule fixed only for the official debate. Like in a sport or in a game, you say, okay, as long as you're playing the game, you have to play by those rules. As long as you do science, that's what you have to do. What a scientist does when they're driving down a road, what a scientist, whether they take LSD or they value beauty and so on in their spare time, what they do over drink, that is all left. They don't have to follow those rules. If they discover scientific things, if they come up with scientific ideas in this way, that's completely fine. But the one thing they need to do in the end, they have to run an experiment. So this is the result of the iron rule, is that scientists agree on the procedure in the official debate. It leaves them freedom by themselves to do anything they want to do in their spare time, and produces as a byproduct this big reef of data. So why does this account for the success of science? Because good evidence is often very hard to uncover. Strevens gives many examples here. It's very difficult often to get evidence for anything. You need to produce experiments that you need to fly to South America, and you need to invest millions of krona and dollars to come up with good experiments. That process can be extremely frustrating. It's extremely boring, extremely expensive. It takes a lot of time. The iron rule forces scientists to keep going with this and produce data that might then become useful later. So it's kind of forces scientists to keep on with this process, even though, and that is useful in the long run. It's useful if you look at the science, this cross-temporal, many-person sort of endeavor. You won't see it in a pretty person, and it forces scientists to engage in that. Okay. I want to end with some consequences of this iron rule that Strevens points out that I would like to discuss with you. So what he thinks is, how then do we get, if the this iron rule is so irrational, how do we get scientists to believe to do it? I mean, in other words, like there comes in you, student, new to physics, and you have all these ideas. Wow, philosophy is like fascinating, discovering the nature of the universe and all that, and I'm interested in all this. And he says, what happens when you study science is you get basically drilled into this iron rule. You repeat it again and again and again in the classroom and elsewhere, and again in what your teachers tell you, that it would be bad, very bad, not to try to distinguish hypotheses by an experiment. And it again and again repeated, that as if they're sort of preachers. You find so many scientists saying philosophy has tried to discover the nature of this and that for many thousand years, but they haven't made much progress. Now we do science, and science means we run an experiment. Nature of consciousness is a thing that I've often heard, the nature of the space and time, everything. The philosophy has worked on it for so long, it's stupid. We need to do an experiment, we need to do science. And so you start believing this because you hear it so often. And as another thing that happens is that you just get to do only these things. It's hard work to just learn how to run these experiments. And through a studying molecular biology, you might easily be deprived of your ability to think philosophically or aesthetically at all. You never really hear about what's happening, for example, in the humanities if you're studying science normally. Now, of course, there are famous exceptions. Einstein, very philosophical mind. Wilson, there's a quote from him. He's an evolutionary biologist, also had lots of philosophical ideas. In Norway, Dag Hessen, very philosophically minded evolutionary biologist. But importantly, it's not that there aren't exceptions. And again, there are exceptions. But again, what the importance that scientists are completely free to philosophize. That's not the iron rule. It's that their philosophizing doesn't really affect the official scientific discourse in those papers. So what Einstein, the philosophy that drove him to discover his theories of relativity, that doesn't count. That doesn't count. What counts is only that there was evidence for it. and Doug Hessen's ideas about how thinking evolutionarily will lead to a better society, it doesn't count. It's not evidence. The only thing that counts are hypotheses that are tested and have won the test. Okay, so you drilled into this. And that means you become a sort of gearhead. We just shut up and calculate. So there's another beautiful metaphor that Strevens has. So he has this image, which is an 18th century image where scientists use new discovery, the air pump, which is a pump that produces a vacuum, and it showed its effect. And here they showed its effect on a bird. You see the bird here on top, and the bird is dying. And so he says that unlike an organism that needs air to breathe, science needs the air to be out, produce a vacuum where there's nothing else but experiments, hypothesis testing. Everything else needs to be sucked out so it's dry and dead, and then science strives. So I think it's a great metaphor of this too. Okay, so then this leads to this question. If the iron rule explains the success of science, and if it requires of scientists to just stop thinking philosophically, aesthetically, and so on, then maybe science really doesn't need the humanities. And then that, of course, raises the question for us. Isn't this course maybe a waste of your time? If you're a scientist, or is it a waste of your time if you're not a scientist, because science works just fine without that kind of reflection that we're doing here? Well, that's something I hope you can think about, and we'll talk about it when we next meet. Okay, thank you.